Boker Tov and good morning, everyone. Today I want to talk about an interesting setting called dynamical systems, where there are lots and lots of problems both inside and outside of mathematics where you can model using dynamical systems. And then we will see how you can use basic linear algebra to already solve a lot of problems inside dynamical systems. But also there are some limitations, and there we will see how the little bit of geometry that we add in the inner product spaces helps us overcome these limitations. Okay, so let's start. So in a very general and abstract way, a dynamical system is just a collection of objects, and they can be in all sorts of arrangements, which we call states, and there is some sort of action which mixes up the objects, or in other words, moves it from one state to the other. So instead of giving you the very formal definition of what is a dynamical system, let's see an example, and I want to talk about 2 by 2 matrices. So in our case, what we see are the objects which are the points in the plane, and I'm going to choose some matrix and I'm going to apply it on the points, and what will happen is the following. So for example, if I apply it again and again and again, you will see this type of rotational behavior. So this is already an interesting dynamical system and also interesting visually, and we can ask all sorts of questions about this system. For example, if I'm at some sort of starting state, what happens if I apply the matrix 10 times? What happens if I apply it 100 times? What happens if I apply it infinitely many times? So again, this needs some sort of definition, what happens at infinity. And after we define what it means, we can ask what really happens there. So this is already an interesting question. We can also ask about what type of behavior can we get. So for example, this is just one matrix. What happens with other matrices? So in this matrix, we see type of rotational behavior. So it is periodic. It repeats itself after a certain amount of time. But we can also expect maybe a chaotic behavior. So everything goes haywire and you don't know what happens. Or maybe it is not periodic and it is not chaotic, but after we applied it again and again and again, then sometimes at infinity it converges to something. Maybe it converges to one point, maybe it converges to this rotational behavior, or all sort of other behavior. So this is in general, but we can ask about these 2 by 2 matrices, what we can see there. So we already see one behavior, this is the rotational behavior, but there are other behaviors as well. So for example, we have this type of behaviors where all the points move in a parallel lines. So this is another type of behaviors which we call parallel behavior. Another type of behavior that you can get in 2 by 2 matrices is the following. So you can see that if I look at some point, it moves at the beginning into the origin and then start to goes out. And if you follow this just one point, then you will see that each point follow a hyperbolic curve. So we call this type of behavior, not surprisingly, hyperbolic. So already we see that just in the 2 by 2 matrices, just in this very simple dynamical system, we have these three distinct type of behaviors. And actually, if you remember what you did in your basic linear algebra course, then you already have all the information in order to understand these three types of behaviors. Right? These are basically the eigenvectors and eigenvalues of the matrix. In any case, if you remember or if you don't, in the description of this video, there is a link to this program with the code and my explanation of what happens there. Okay, so this is the 2 by 2 matrices. Do we have other more dynamical systems? So of course we can talk about 3 by 3 matrices and their action on our three-dimensional world. We can talk about n by n matrices and their action on the n-dimensional world. We can talk about complex numbers. So up until now we acted on the real world. We can talk about complex world. We can talk about finite fields and many more. So we already see that just talking about linear algebra dynamical systems, we have a lot of systems, and at least visually they can look very nice. But now I want to show you that even if we leave the linear algebra world alone, there are still many interesting dynamical systems. So let's see a couple of them. So one type of a very interesting dynamical system is about card shuffling. So for example, I have here a deck of cards, or at least one suit from a deck of cards. And again, the cards are the objects of the system, their arrangements is the state of the system, and the shuffling itself is the action. So for example, let me give you two types of shuffling, very basic shuffling. So one type is just take the first card and move it to the end of the deck. Right? This is a very simple shuffling. Another one is just switch between the first and the second card. So I take the first card and I put it instead of the second card. And now maybe I want to add a little bit of randomness. So I take a coin and I flip it. And if I get heads, I take the first card and put it at the back. I get heads again, I take the first card and put it at the back. Or I get tails and then I switch between the first and the second card. So these are two shuffling, which I choose randomly. And I can do it again and again and again. And ask lots of interesting questions about this type of shuffling. So for example, how many times do I need, how many shuffles do I need until the deck is actually shuffled? And there are two questions there. What does it mean to be actually shuffled? And once we have the definition, how much time it takes to get there. So again, we have a very interesting dynamical system and a very interesting question that we can ask about it. By the way, this was just one suit of cards, so there are 13 cards, meaning we have 13 factorial states, which is already big. But if we talk about the full deck of cards, we have 52 cards, then we have 52 factorial, which is a huge number. I mean, I would call it an astronomical number, but I think that most astronomical numbers are actually tiny in compared to it. Right? So this is a dynamical system. It's a huge dynamical system. Okay, so this was card shuffling, where at each step we chosen the next shuffle randomly, and I want to generalize a little bit this setting to a much larger framework, and this is usually called random walk. So let me give you another example of a random walk, and I want to talk about people in an amusement park. And for that I need another animation. So let's say that we want to build an amusement park. And we start with just 5 rides. We have 1, 2, 3, 4, and 5. And we build some roads between them. So let's do this road, and this road, and this one, and this one. And just to make it a little bit clearer, let's change the color. So I want it to be, okay, this type of sky blue. Okay, so we have an amusement park, and now we had some people in. So here we have this white dot. And the way that the people choose where to go next, so each time they go on a ride, and once they are done with it, they choose one of the roads randomly and goes to the next ride. So we saw it was on the red ride, and he chose to go right and went to the purple one, and now he must go back because there is only one road going out, and he went back to the red line. Okay, so this was just one person. Let's add many more people. And each one of them is going to do this type of random walk. They go on one ride, and once they are done, they choose the next one randomly. And now you are the owner of this park, and you want to build a food stand next to one of these rides. And the question you ask yourself is, next to which ride do you want to do it? So the answer is probably you want the ride where there are the most amount of people on average. Because maybe here at a specific point of time there are lots of people here, but you want it to do an average. And now if we look on this simulation, let's just move it a little bit inside, and you ask yourself which one of them on average has the most amount of people, then you will probably see that actually this red one has on average the most amount of people. And at the very least, you can see that maybe this red one has more people than this green one. So this is really, again, a very interesting question about random walks, right? About dynamical systems. So what happens if I add another road, something like this? How does it change the random walk? How does it change the ride that there is the most amount of people? Or maybe you want to ask which one of them has the least amount of people, again, on average. So this was a question about people in amusement park, but you can probably see that you can apply to many other problems as well. For example, we can talk about following the money. Maybe the points that we see here is actually money, they are dollars, and the states, the nodes here are the people or companies, and the money more or less moves randomly between one person to the other, or between one company to the other. And then you can ask, which company has on average the most amount of money? Which company has the least amount of money? So this is following the money. Maybe you can ask about website exploration. So maybe each one of these nodes is a website, and the person who goes onto the website chooses a link randomly and goes to the next website and do this random walk. So again, it does it again and again and again. and you want to ask which website has the most amount of visitors on average. And maybe you can use it in order to build your search algorithm. So you can see that this is a very, very general, and you can apply it to many, many places. Okay, so we have this card shuffling, we have this random walk, and of course we had before the linear algebra. And what I claim is that actually the card shuffling is a random walk, and we already talked about it because each state is basically a node, it's something like this, and we move from one to the other by choosing randomly where do we go. But I also claim that every time you have a random walk, you can actually model it using a linear algebra dynamical system. So let's see how to do it. As an example, let's look on the following graph. So we want to do a random walk on this graph. So we move between the 1, 2, 3, and 4 vertices along the edges. And let's say that we start at the first vertex. So just to model the state that we are in, we model it using a vector. So we have 1, 0, 0, 0, because we are on the first vertex and not on the second, third, and fourth. And what we do in the random walk is we choose randomly between going to the second vertex and to the third vertex. Now, instead of thinking about just one person doing it, let's think about it as a whole population. It's 100 people on the first vertex. And then we split them to half. And half of them go to the second vertex and half of them going to the third vertex. So this is again another state of our random walk. And again, we can model this using a vector, right? We have 0, half, half, and 0, because 0 of the population in the first vertex and then the fourth vertex, and half of the population in the second vertex and in the third vertex. And now we can do it again and again and again. So for example, if you are in the third vertex, we have two options. So we split the population into two. If you are in the second vertex, there are three options. So we split the population into three. And then from the third vertex, half goes to 1 and half goes to 2. And from the second vertex, third goes to 1, third goes to 3, and third goes to 4. And again, if you check how much of the population is in each vertex, you will get this nice vector of 5 over 12, 1 over 4, 1 over 6, and 1 over 6. And you can see that I can do it again and again and again. Okay, so we already know how to model the states of our dynamical system using linear algebra, using vectors. But I claim that we can also do it for the actual action. So for example, in order to move from the first vector to the next one, we only need to multiply by this matrix. So I need to tell you how I build this matrix. So for example, the first column, I can derive it from the first vertex. So the first vertex either move to the second or the third by half and half. So the first column is going to be 0, half, half, 0, because we have 0 chance to move to the first or the fourth vertex, and we have 50% to move to the second or the third one. Similarly, if I want to understand the second column, it comes from the second vertex, because I have a third of a chance to go to the first, third, or fourth vertex. So I have third in the first, third, and fourth coordinate of the vector, and 0 in the second one. And similarly, this is how I construct the third vector and the fourth column. Okay, so now we know that you can move from the first state to the second by using matrix multiplication. But I claim that if you want to move from the second to the third step, you also use the same multiplication by the same matrix. And also if you want to move from the third to the fourth, or if you want to move from the n step to the n plus 1. So in general, if you want to understand the action, this random walk, all you need to understand is this matrix A. So again, we started with a general dynamical system or general random walk, and we managed to model it using by matrix multiplication. So now, if you want to apply the random walk again and again and again, then basically the question that you want to ask is, what is a to the power of k? So you started with random walk, and you ended with a very, very basic question about linear algebra. Okay, so let's try to actually understand what is a to the power of k. Okay, so let's start with the simplest example. Let's take a 2 by 2 matrix and take k equals 2. So I just want to compute the square of a 2 by 2 matrix. So this is not too hard, right? I can actually write it down. However, if I go to a 3 by 3 matrix and I want to write it down, I cannot do it. This is just too big to write it down. Maybe I can do it on the full screen, but if I go to a 4x4 matrix, this is already done. I don't think that I can even write it on the full screen. And 4x4 is small. In the type of problems that you talked before, you can easily get a 10 by 10 and you can get 1000 by 1000. I mean, if you want to do the search algorithm, then you have thousands of websites. So you can think about a 1000 by 1000 matrix, and you want to take the square of these matrices, you want to take the k power of these matrices. This is huge. And more generally, if you want to multiply an n by n matrix by itself, then you need to compute n square entries, and each one, in order to compute them, you need to do n addition and n multiplication. So basically you need about n cube steps. And n cube, when n is very large, when n is 1000, when n is 1 million, this is huge. So you really don't want to do just the standard multiplication. Now, luckily for us, we do learn basic linear algebra in our first semester, and there we have a very interesting trick. So there is an idea, and the idea is you do diagonalization. So let's remember what happened in diagonalization. Well, you try to write A as a P times D times P minus 1 if you can, where D is a diagonal matrix. And if you manage to do it, if you do this type of diagonalization, then a to the power of k is p d p to the minus 1 to the power of k. And you can just write p d p to minus 1 k times. And then you notice that p to the minus 1 times p cancels each other out. And it happens again and again and again. So by the end of it, you just get p times d to the k times p to the minus 1. And d to the power of k is much easier to compute than a to the power of k. But this is just d1 to the k, d2 to the k, until dn to the k. So let's just write it down there. So when we want to multiply a to the power of k, this is just p times d to the k times p to the minus 1. Now, this is just a formal definition of diagonalization. However, the way that you should think about it, or at least the way that I think about it, is that when you have matrix multiplication, let's say on a 100-dimensional space, the multiplication just takes this 100-dimensional space and mixes everything up. So this is a very, very large operation. It is very hard to understand. Saying that your matrix is diagonalizable means that if you look on this vector space on the right angle, you can decompose it into 100 one-dimensional vector spaces, and your matrix acts on each one of these one-dimensional vector spaces separately. So understanding this big action is equivalent to understanding each of these very, very small actions. So we have 100 very, very small actions. Each one of them is very simple to understand, and we can combine their solution in a very, very easy way. So again, the whole point of diagonalization is a divide and conquer. We have a very, very large problem. Instead of trying to solve it, we divide it to very small problems, solve each one of them separately, and then combine them back together. So this is a diagonalization. Very, very interesting idea, very, very good tricks that we learned already at the first semester in basic linear algebra. And again, this is very useful in many, many places. However, not all of them. For example, one of the limitations is the question, what about P? Because remember, the matrix D, or the elements on its diagonal, are the eigenvalues of A, and P are the eigenvectors. And it can be a very, very large matrix. For example, in the card shuffling problem, we have 52 cards. So P is going to be a 52 factorial on 52 factorial matrix. This is going to be huge. And we don't want to multiply these two types of matrices. And here is where inner products shine. Because if you add a little bit of geometry, then suddenly you have a little bit more structure, and you have lots of tools that you can use, and maybe you can use them in order to say something about this problem. So just to give you a little bit of intuition, if you remember when we talk about our three-dimensional world, usually our basis is something like that. We have 90 degrees between any pair of vectors. So for example, if I already gave you the blue vector and the red vector, and I'm telling you find me the green vector, you basically only have two choices. Either you take the vector on the screen or it's minus. Right? So this is a very, very rigid structure. So maybe this rigidity, maybe the new tools that you get from this new structure can help us, and they will actually help us in order to solve this type of problems. Okay, so again, we're going to add geometry, and it's going to add a lot of structure for us. We're going to add distances, and we're going to add angles and limits, and further along the way, we can talk about derivatives and maybe integrals. And again, all this new structure just helps us in order to solve this type of problem. Okay, so this is what we're going to talk about in our inner product spaces. A little bit more structure, lots more results. And just to give a little bit more spoiler to other courses as well, if you add a little bit more structure using symmetry, then this is basically when we get the Fourier transform, which is again one of the most basic and powerful tools that every engineer should know. Okay, so this was a more in-depth application of inner product spaces, and we will see how to use them along the course. And in the next video, we will actually start with the actual material of the course. And I will see you then.